Welcome to Brain Vision.
For this situation, we're asked to consider a coaxial cable with a solid inner radius conductor of a radius R1, and it's surrounded by a concentric cylindrical tube of an inner radius R2, and then an outer radius R3. You can look at figure 42 to get a visual representation of this. So it carries a current I naught distributed uniformly across the cross section. So I naught is carried uniformly across. And it says to determine the magnetic field at different distances r from the axis. For part A, it's when r is less than r1. Okay, so I'll indicate this as part A, when r is less than r1. So first thing we're going to do is we're going to use Ampere's law, because Ampere's law will give us the magnetic field from a current. So Ampere's law says that the integral over a closed loop, so that's what this little circle represents on the integral. Let me redraw that to make it look nicer. That looks better. The integral of B dot dl, where dl is the unit length here, is equal to mu naught, magnetic permeability of free space, times I enclosed. So we'll call this I, E, and C. Okay, so we carry out the integral on the left side. This simply ends up becoming magnetic field times the area of the integration, which is 2 pi r, since we're just integrating over the surface here. The area is actually it doesn't give area. 2 pi r gives you the circumference of the circle that we're integrating over. And so this b times 2 pi r, since the 2 pi r is what comes from the integration over the closed circle, is still equal to mu naught times I enclosed. So we can rearrange this to solve for b in general, and we find that b is equal to mu naught times I enclosed divided by 2 times pi times the radius r, where r is the distance we are from the axis, the distance we're trying to determine the magnetic field strength at. So the next question becomes then, what is I enclosed? Okay, so the current enclosed in the Gaussian surface is the product of the area of the Gaussian surface and the current density. So we can say that I enclosed here is equal to the area A times the current density J. Well, what's the area here? The area, since we're considering it to be circular, is just going to be pi r squared, right? And the current density is going to be the current that's running throughout, I naught, divided by the area in which it's running. We'll call this area A prime. But since we're considering it when r is, when r is less than r1, this A prime is just going to be the area of the R1 section, which is just pi times R1 squared. So now we have I enclosed. We can plug that back in above into our magnetic field, and what we end up with is mu naught. I enclosed would be pi r squared times I naught divided by pi r1 squared. So we can plug that in. So this is mu naught over 2 pi r. And then this is going to get multiplied by pi r squared. And then times I naught divided by pi r1 squared. So we can cancel out the like terms like the pi's and the r's. Notice that r1 is only in one place in the denominator there, but there's an r squared on top as well as an r on bottom. So if we cancel out the like terms, what we end up with is mu naught times r times I naught divided by 2 times pi times r1 squared. We can go ahead and box that in as our solution for part A. Part B wants us to find the magnetic field, but this time for the regions where R1 is less than R and R is less than R2. So essentially between R1 and R2. Okay, and we'll indicate this as part B. It's the exact same equation that we're starting out with, for the magnetic field, where B is equal to mu naught I enclosed over 2 pi r. So I'll point to it here, or maybe I'll just underline it with the red line here. So this equation that I'm underlining here, this B equals mu naught I enclosed over 2 pi r. This is the one we're going to keep referring back to, but in each case, we just have to figure out what the I enclosed is. Well, in this case, the I enclosed is pretty simple to find. It's just equal to I naught. Since in that region, the current that's running is just the I naught current. So all we have to do in our equation for the magnetic field is replace I enclosed with I naught, and we've solved for part B. So this is mu naught times I naught divided by 2 pi r. Again, that's for the region between R1 and R2. Part C would like us to calculate the magnetic field in the region where R2 or R is between R2 and R3. So when R is between R2 and R3, the enclosed current is equal to I naught multiplied by the ratio of the differences between the area made by the distance the magnetic field is trying to be calculated at, that R value, not R1, R2, or R3, but the R value we're trying to calculate the magnetic field at, that area minus the area A2, the area that's made by the R2 value. And the reason this is true is because here R is greater than R2, right? And then this is going to be divided by the difference between the area A3 minus A2. And that's because A3 is also larger than A2. So we can plug in the values for these areas, where A is pi r squared, A2 is pi r2 squared, and A3 is pi r3 squared. So you can see that each one has a pi term for all these areas. So that pi term is just going to cancel, and we can just simply write the r term. So this is r squared minus r2 squared divided by r3 squared minus r2 squared. Again, I canceled all the pi's that would normally be written in front because each one would have a pi term, and we can just cancel those out. Okay, so now we just need to replace our I enclosed in our equation for the magnetic field with this value that we just found, and we've solved for the magnetic field in part C. So here, B is equal to mu naught over 2 pi r, mu naught times I naught, right? Because I enclosed still has that I naught value, but then we also have this r squared minus r2 squared divided by r3 squared minus r2 squared. All right, and we can go ahead and box that in as our solution for part C. Okay. Part D would like us to find the magnetic field in the region where R is greater than R3. Well, when R is greater than R3, the I enclosed value is equal to 0. Therefore, if I enclosed is equal to 0 and we plug 0 into our expression for B, then B is also going to be equal to 0. So part D is simple. And we can box that in. And then part E would like us to graph the magnetic field as a function of R. So we can go ahead and do that, where the y-axis is our magnetic field, B, and the x-axis is our R value. So we have R1, right? We have R2, and we have R3. Well, if we go back to look at the magnetic field in the region where R is less than R1, we found that it was mu naught R times I naught divided by 2 pi R1 squared. But again, here, we're considering where R is less than R1. So as R increases, if you look at that expression, R is linear, or excuse me, B is linear with R if you look at that expression, right? So we're going to increase at a linear rate, something like this, until we hit a maximum value at R1. Now we're in the region where R is greater than R1 but less than R2. That's what we found in part B. So when R is greater than R1 but less than R2, it's mu naught I over 2 pi R. So it decreases as R increases. So now, if we go back to our graph, this is going to start to drop. Okay, then we get to the region where we're between 2 and 3, right? Which is what we found in part C. So if we go back to our solution for part C, let's see, here it is. At the top, we have R squared minus R2 squared divided by R3 squared minus R2 squared. So this is a little bit more difficult. So I went ahead and just kind of plugged this into a graphing calculator, and it still decreased, but it looked something more like, let me go back to the graph page, looks something more like this. Faster rate, went down, and then once you hit R equals 3, the magnetic field decreases to 0. So it goes to 0. And that is the solution for part E.